About 13.8 billion years ago, the universe was incredibly hot and filled with elementary particles. As the universe expanded and cooled, protons, neutrons, and eventually atomic nuclei, atoms, and matter formed. About 9.2 billion years later, the Earth, our home, was born. Unraveling the microscopic world of particles and atomic nuclei means exploring the history of the universe itself. The Institute of Particle and Nuclear Studies, IPNS, located in KEK, is a research institution that advances our understanding of the physical world from microscopic particles to the whole universe, by developing theories and performing cutting-edge experiments. At IPNS, we pioneer new theories that encompass the standard model of particle physics which physicists have been developing for over a century, and test them through experiments. The IPNS conducts multilateral research spanning from the microscopic world to the universe through 5 areas: energy frontier, theoretical physics, particle astrophysics, flavor physics, and hadron nuclear. The Belle II experiment is searching for new physics phenomena that could hold the key to solving the mysteries of the universe. By precisely studying the decays of particles produced by the Super-Kamiokande accelerator, in which we produce extremely rare phenomena of the universe such as the breakdown of the particle-antiparticle symmetry. The Belle II detector is about 8 meters in width and 8 meters in height, with a weight of around 1,400 tons. It contains multiple detector components optimized for various measurements in a multi-layer cylindrical structure around the collision point of the Super-Kamiokande electron and positron beams. Belle II is an international collaboration of over 1,100 researchers from 125 universities and research institutions in 28 countries and regions, and KEK is the host lab.
僕は2021年からベル実験に関わってます。学生の時にミオンというレプトンの実験をやっていたんですけれども、ベル実験だとより重いレプトンを使ったことができるのでベル実験を選びました。今は過電粒子を見るための CDC という検出器に携わっています。これは一人だとどうしても開発や運用ってできないんですけれども、一人じゃなくてみんなでワイヤーやりながら開発や運転をして、それでみんなで作ったもので何か粒子を見れて、さらに物理事象も観測できた時に楽しさを感じます。
Energy frontier experiments use high-energy accelerators to recreate and measure particles and phenomena that governed the early universe. The LHC Atlas experiment at CERN near Geneva, Switzerland, is now investigating the Higgs boson and searching for new particles. The IPNS Energy Frontier Group plays a central role in ATLAS, from the construction of the detectors to physics analysis. Detectors shown in red are Japan's contribution. IPNS collaborates with domestic and international universities and research institutions to advance detector development for future energy frontier experiments such as the ILC, International Linear Collider. In energy frontier experiments, we are not only searching for unknown particles and investigating the properties of the Higgs boson, but also advancing research towards grand unified theories and theories of everything that aim to explain the origins of the universe. T2K is a long baseline neutrino oscillation experiment. Neutrinos produced at the Japan Proton Accelerator Research Complex, JPARC, in Ibaraki Prefecture, are observed at the Super-Kamiokande detector 295 km away in Gifu Prefecture.
Neutrinos are very special because they're the most numerous fundamental particle that we know of in the universe, and yet they're the particle about which we know the least. For example, we know neutrinos are very, very light, lighter than any other particle that we know of, and yet we don't actually know what their mass is. The reason we know that they're very light comes from a very special quantum mechanical effect called neutrino oscillation. And in 1998, Super-Kamiokande gave us the first evidence for neutrino oscillation, which helped us understand that neutrinos have mass, but that we know that that mass is extremely light. We continue with these studies today through the T2K experiment. And the T2K experiment allowed us to understand many more interesting things about neutrinos.
I joined the T2K Collaboration about 2 years ago. And one of my motivations for joining this collaboration was the opportunity to work on detector electronics, the design, the building, the installing, the testing. And this is really exciting. I think it's kind of like a puzzle that you have to solve. T2K, which is such a large international collaboration, there are so many talented experts on the experiment. And as a graduate student especially, I think it's a great learning experience. And I hope to learn a lot over the next couple of years about neutrino physics and particle physics generally, and get to work with some really great people.
こちらが ND280 と呼ばれる全地検出器の一つです。深さ 33.5 メートル、直径 17.5 メートルの実験ホールの中に設置されています。ND280 はニュートリノターゲットから280メートル下流に設置された検出器群で、振動前のニュートリノを測定しています。中央に見えるのが新しい標的兼非積検出器のスーパー FGD です。スーパー FGD は1センチ角のシンチレーターキューブ200万個と、それを3方向に貫く波長変換ファイバーからなる検出器です。今まで見ることのできなかった低運動量の粒子や大角度に散乱された粒子を捉えることができるようになります。
現在こちらでは次のニュートリノビームへ向けて新型検出器の最終調整を行っています。アップグレードされたことによって今までうまく捉えることのできなかったようなイベントについてもより精密な解析を行うことができるようになるので、今後この世界に一つしかない検出器を用いてどこまで精度の良い結果を出し、ニュートリノの謎に迫ることができるかとても楽しみです。
JPARC hosts the Hadron Experimental Facility. Hadrons are types of particles which experience the strong interaction. At the Hadron Experimental Facility, the origin of matter is investigated on the microscopic scale to answer questions such as, what are the ultimate building blocks of matter? What forces bind them together? The Hadron Experimental Hall is the central building of the Hadron Experimental Facility, 58 meters wide and 56 meters long. It houses the beamlines that guide the proton beam from the accelerator. Each beamline has its own experimental area. In addition to studying the nuclear force, we are conducting the Koto experiment, which is searching for a rare decay mode of the neutral K meson which breaks CP symmetry, and the Comet experiment, which is exploring muon to electron conversion. Discovering these extremely rare phenomena would be a remarkable sign of the new physics beyond the standard model. This universe began from a rapid expansion known as inflation, before the ultra-hot Big Bang. Observations of the oldest light in the universe, the cosmic microwave background, CMB, are being conducted to seek definitive evidence for this theory. If we can observe a specific type of polarization mode within the CMB, it would serve as definitive evidence for inflation. The Experimental Cosmophysics Group is dedicated to studying and observing this effect from the Earth and space. In quantum mechanics, various particles can briefly appear and disappear, known as the quantum loop effect. This effect directly appears in the particle's anomalous magnetic moment, G-2, and electric dipole moment, EDM. The Muon-Neutron Group is approaching the new physics laws not included in the standard model through precise measurements of G-2 and EDM. The Wako Nuclear Science Center, located at Riken in Wako, Saitama, artificially creates short-lived nuclides by using KISS, an internationally unique nuclear experimental device developed by KEK, and provides them for joint-use experiments. Collaborating with the Riken Nishina Center for Accelerator-Based Science, we aim to discover new isotopes and elucidate the origin of heavy elements in the universe. What laws govern the universe? How did the universe begin? Various experimental projects at IPNS are dedicated to unraveling these fundamental questions. Underpinning these projects is theoretical research. What are the laws of particles? What are the properties of nuclei? What is the true nature of dark matter? What defines space, time, and quanta? At the Theory Center, through a blend of experimental data, mathematics, computational tools, and imagination, we are on the quest for the ultimate theory of nature. The Instrumentation Technology Development Center was established for the operation of the Instrumentation Development Test Beam Line as a hub for the development of various particle detectors and for researcher exchange, working with university collaborative users. Our goal is to nurture new ideas by facilitating interactions among researchers from a wide range of fields, without confining it to particle and nuclear physics fields, and to create a place for young researchers with innovative ideas. Collaboration with international researchers is crucial to advancing research into particles, nuclei, and the universe. From all over the world, researchers regularly visit IPNS to collaborate on various physics studies and experiments. IPNS researchers are dedicated to acquiring new knowledge that will become a common property of all humankind through collaboration and competition with exceptional researchers from around the world. We are also committed to fostering outstanding researchers who will advance the progress of research in the future.